Okay, Antonio, hopefully that this explanation will help work. I'm going to assume that you know how to solve a derivative, like do like the power rule. I'll go over it briefly so we can kind of just breeze through that part. But this right here is looking for a maxima and a minima using a revenue function, and it's giving you nothing. It's a word problem, so it's a pain in your butt. But let's go over the power rule really quick. So the power rule says any number raised to a power, what you can do to find the derivative of that function or of that term is you bring down that number, the exponent, you multiply it by the number there, and then you subtract 1 off the original exponent. So let's put this in action. So if you have x to the third, step 1, you bring the 3 down, and you multiply it to x, and then you subtract 3 by 1, and what this looks like is 3x to the second. So that should be a review. For this equation, we're going to have something that looks like this. No, I don't want that. Let's just stick with 3. So 3x to the third. What we do in this case is we bring down 3, we times it by 3x, and this is still to the third minus 1. This is going to look like 9x to the second. Does that make sense? So 3 times 3, and then you subtract 1 off of the 3, and it becomes a 2. So this is the function, and this is the derivative, or the slope function, or the whatever you want to call it. That's what that is. Okay, I'm going to make this smaller into the side, like over here. So I'll zoom in if we need that. Okay, so step 1 here is I wrote out what we know. So number 1, we know the price of the boat. I denoted that as P. Number 2, we know the number of boats sold. I denoted that as quantity. And it's not as clear as you think it is. So let's go over. So the price of the boat is $45,000. Yes. Almost. We'll come to that in a second because this question is very tricky. The number of boats sold is 3, and it's per month. So wait, sorry. The number of boats sold is 40, but it's increasing, so it's going up at 3 boats per month. So I wrote up here the T. T means month. Let me show you what this equation says. So Q of T, that's what this will be called from now on, is 40 boats plus at an increase of 3 per month. So we'll just leave this open for now. That's a T, just imagine. So let's say that it's March. How many boats did they sell in March? So the answer is March is the third month, so you put a 3 there and a 3 there. So it's 40 plus 3 times 3, which is just 9. 40 times 9, or plus 9 is 49. So in March they sold 49 boats. So we can guess in February they sold 46, and in January they sold 43, and so on and so forth, with that pattern of increasing at a rate of 3 per month. So that's how that works. That's that function, if that makes sense. That's why we have the T there. Okay. Sorry, my thing's freaking out here. All right. The next function we have is the price per boat. So right here we have $45,000 per boat, and we're looking for how much the price could drop before the monthly revenue starts to drop. So we're going to use R at the rate of drop, rate of drop. Okay, so 45,000 minus the rate of drop times the month. Well, month is denoted as T. I don't want to use M because M is slope. Okay, so that's everything, all the setup. Now we have our equation here, which is revenue equals price times quantity. So we have price and quantity. These are our two functions. So revenue function R of T equals P of T times Q of T. just plug it in. We have R of t equals P of t, which is 45,000, minus R of t, and then it's multiplied by Q of t, which is 40 plus 3t. Okay, so now you're probably like, if you're like me, you'd probably get stuck here because you're like, what do I do? And the answer is we're just going to FOIL. If you remember FOIL from past math classes, these are set up in a way that there's terms and there's, what's it called? Factors and all sorts of things. So if we look here, there's a minus there and a plus there. Those are really important because they kind of separate out the function on the inside. So we can use this to kind of act like as if it was something like this, right? Which would equal this. And that's because of FOIL. So we're going to use FOIL in this case to help us solve or help us simplify the equation. This won't solve anything. It will just simplify it, so then we can solve. So we're going to times 45,000 by 40. Okay, and this number is going to be 1.8 million. So to write it all out. Okay, we're going to add it to 45,000 times 3 of t, so it's first, and then we're going to outer. 45,000 times 3 of t is 135,000 t. Okay, next is to do the inner, which is negative r of t times 40. I don't know why I circled it that time. So that's going to be negative 40 RT. Okay, and then the last one is negative R of t times positive 3t, negative 3r t squared, because there's two t's. So this is our new simplified revenue function. Yeah, these two are the same. These two do equal each other. And we're going to manipulate it even further by now taking the derivative. So we're going to be using our power rules we went over earlier. So the derivative is shown like this. I don't know why I wrote an x there. It's actually a t. Okay, so to take the derivative, we're going to use the power rule. Any just plain number is 0. So if it's just a number and has nothing else added to it, like if it's like the derivative of 3 is 0. So the derivative of 1.8 million is 0. It doesn't matter how big or small the number is. If it's just a regular number, it's 0. But this one has a unknown, a variable attached to it, a t. So what happens here is we're just going to use the rule we learned earlier. So we bring down the 1 in front of there. So 135,000 times 1 is because t is raised to the power of 1. 135,000 times 1 is just 135,000. 1 minus 1 is 0. Any number raised to a 0 exponent is just going to be 1. So then it's 135,000 times 1 again, which is just 135,000. So that's the long way of explaining that any number that has a variable that's raised to the power of 1 is just the number, so the variable disappears. Okay, same process here, except r is on the inside, so we're going to just do negative 40 r, which is our rate of drop. This one we're going to bring down the 2, multiply it by negative 3. 2 times negative 3 is 6. There's an r there, and the t, 2 minus 1 equals 1. We don't have to denote a 1 on top of the t as like an exponent. So here we are with our derivative, and what this shows is the slope of this function. So now with this function we can plug in and find the slope at any point along the line. So if the function looked like this, these are the months, we can see like on this month the slope was this, and on this month the slope was that, meaning like the change in y over the change in x, right? Which is rise over run. Okay, I'm sorry, I'm just giving a lot of extra information because it might be helpful. So this is the slope function. So anything you plug into here for t will give you the rate of change in this function in particular. The problem is we still have r's. So we want to find the rate of drop, right? We want to find like the biggest drop. So what this means is that we're going to be looking for a local maxima or minima. And we can do that by zeroing out the function. So the way to zero out a function is to just make it equal 0. So right here, oops. So this function now equals 0. So wherever this function equals 0 is where there's going to be maxima and minima. And what that means is, how do I explain this best? I don't know how far you are in your class, so I'm trying to like think about where, like, what your understanding would be. If it's just a derivative, then don't worry about local maximum and minimum right now. Let's just assume you don't know about them and just tell you to set it to 0. So you're going to do a 0 set equation. We're going to make t time because we're looking for the fastest. We're going to make that start at 0. So t equals 0 in this function. So this is going to be 0. 0 times r is 0, and then 0 times 6, negative 6 is 0. So this becomes 135,000 minus 40r equals 0. The 6 gets dropped because it has that t attached to it. Okay, now what we do is just basic algebraic manipulation. So, like this. So it's 135,000 equals 40r. You see how I did that? I added 40r to both sides to make sure the r sticks with it. And then you divide by 40. I'm going to switch the r over here because I hate to write the other way. So 135,000 divided by 40 is 3,375. This right here is your answer. So you're looking for, once again, we wrote it up here, the rate of drop. What is the fastest the price could drop before the monthly revenue starts to drop? This is the fastest the monthly that it can drop before the monthly revenue starts to drop. Okay, so this is $3,375 per month is the rate of drop, if that makes sense. So that's what you're looking for. The keynote here is to realize the steps that I took. So the first thing I did is I found out what I knew. So right here is what I knew in my variables that I used. Second step was to set up the equation and to simplify. The third one was to take the derivative of that equation or find the slope equation. And then the fourth step was to set to 0 and to find your answer. So hopefully this helped. If you want me to go more into local maximum and minima, I'd be happy to. I can do that. So just let me know.